Hi everybody. In this video I want to do an example problem involving Faraday's law in which we have a loop in a changing magnetic field. In some problems we've used the changing magnetic field to try and determine the current that's induced in the loop. In this problem we're going to change things around. I'm going to give you the current that's induced in the loop, and we need to infer information about the way the magnetic field is changing. Alright, so here's the problem. Let's imagine we've got a square loop of side 0.250 meters on each side, oriented in the XY plane. So the plane of the loop is in the XY plane. The Z direction will be out. Let's say that the loop has a resistance of 0.100 ohms. Let's say that the induced current produced by the changing magnetic field, whatever that changing magnetic field may be, the induced current is going this way around the loop in the XY plane and has an amount of 0.400 amps. So the current has an amount, 0.400 amps, and is going this way. And so from this information, our task is to try and figure out the rate of change of the magnetic field. And the way I've expressed this, I've asked us to calculate the rate of change of the Z component of the magnetic field. You might ask, well, why haven't I asked about the rate of change of the X or Y components of the magnetic field? And the answer to that is we can't get any information about that from this loop. The only flux through this loop that magnetic fields are going to produce is going to be due to the Z component of the magnetic field. The X and Y components of the magnetic field will be in the plane. They won't produce any flux. So the only change in flux can come from a changing Z component of magnetic field. Changing the X and Y components of the magnetic field, neither of those components of the magnetic field produce any flux, so changing them won't produce any changes in flux. All right, so we won't know anything about the way the X and Y components of the magnetic field are changing from this problem, but we can get information about how the Z component of the magnetic field is changing. All right, we're going to want to be careful with our sign conventions. So I'm going to choose my area vector. I could choose it into the page, into the board, but I'm going to choose it out of the board. So I'm going to choose my area vector to be in the Z direction. So I'm going to write it as area vector equals area magnitude, which is just the area, times the Z hat direction. Now we might do some advanced thinking about this. What about the current? The current has an amount, 0.400 amps, but remember, there's a sign convention that we need to be careful with. So there's a right-hand rule relationship between the direction of the area vector and the positive direction around the perimeter. So my area vector is out. I stick my thumb in the direction of the area vector. My fingers wrap around in the positive sense of the perimeter path, which would also be the positive sense of the current. All right, so if the current was positive, it'd be going this way. But the current's going this way, so the current's actually negative. So if I'm going to do a calculation and be really careful with my Faraday's law stuff, this current is hiding a minus sign. All right, and we'll use that later. Okay. So let's express our magnetic flux. I'm going to do that because I want to put that into the the rate of change of flux with respect to time that goes into Faraday's law. So let's just express this out. I can write my magnetic field in general as an X component times X hat plus a Y component of the magnetic field times Y hat plus a Z component of the magnetic field times Z hat. So I'm going to do that right here. I'm going to take the dot product with the area vector, which is just the area itself, the scalar area, times Z hat, where that area is a positive number. Okay, so X hat dot Z hat is 0, Y hat dot Z hat is 0, and so the flux expression is just going to pick off B sub Z times Z hat dot area, just the absolute value of the area, times Z hat. Z hat dot Z hat is 1, and so my flux is just going to be B sub Z times the area. Okay, so now I can plug that into my Faraday's law expression. I'm going to assume, I should have said at the outset, let's assume that this is an instantaneous current. So at this particular instant in time, this is the induced current. It's got this amount, and it's going in that direction. All right, so if this is instantaneous, I can use the instantaneous Faraday's law. All right, I'm just going to plug this in for the flux. And the area is a constant, so I can pull it out. All right, I can take one more step. This induced voltage, the Faraday's law process is producing an induced voltage in this loop. That's the voltage gain, and then the voltage is dropped across the resistance of the loop. So I can replace this with the induced current times the resistance of the loop. And then I can solve for the rate of change of the magnetic field. It's not an equal sign, just an arrow implies. Okay, so we're almost done. All I've done is I've divided both sides by the area. I've divided both sides by the minus sign, solve for the rate of change of the z component of the magnetic field with respect to time. All right, so I got to be careful. This area I can plug in 0.250 meters times 0.250 meters. That'll go here. For the resistance, I can plug that in. That's 0.100 ohms. And then the current now, this current is hiding a minus sign, as I said earlier in the problem. So for the current, I need to put in minus 0.400 amps. All right, so if I plug all those things in, I'm going to squeeze that number in right here. Plus 0.640 Tesla per second. And that's the rate of change of the z component of the magnetic field with respect to time. Okay, let's do a reality check. So to get this and infer this, I worked it out using a careful sign convention with Faraday's law, but I can check it with Lenz's law. So taking this seriously, let's work backward and make sure the current direction checks out. So this says that the magnetic field, the z component of the magnetic field, is changing positive 0.640 Tesla every second. So that means, for example, maybe at some time it's at 0 Tesla, and then a second later it's at positive 0.64 Tesla. Every second, the z component is increasing. The z component of the magnetic field is increasing by 0.640 Teslas each second. Okay, so the magnetic field is changing such that it's getting more and more this way. Now, the magnetic field could be into the board. It's either into the board and getting less and less and less, or it's out of the board and getting greater and greater and greater with respect to the z component. Either way, it's the change that matters. So the change in flux is coming out through the loop. All right, so what the current that's induced needs to do is produce a counterflux that's into the loop. All right, the initial this magnetic field whose z component is increasing is producing a change in flux out of the loop. The current needs to produce a counterflux into the loop. For the current to produce a counterflux into the loop, it needs to produce a field through the loop into the board, and this current direction would do that. So I could check that, stick my fingers in the direction of the current going around the loop, thumb points in the direction of the magnetic field that current produces at the center of the loop. That's into the board. That is a counterflux then into the board, which opposes the out of the board flux that produced the current in the first place. So it all checks out. If you want to check the current in another way, stick my thumb in the direction of the current, my fingers would wrap around and they go into the board at the center. So we know that this current produces the proper direction of magnetic field to counter the flux that produced that current in the first place. Okay, so I hope that helps. Thanks for watching.